Hello, this is Gary LaRue, the technical editor at Microwave Journal. It's my pleasure to welcome you to today's educational webinar, Linearity, the Key to Successful Data Transmission in Cable and Beyond. The presentation will be given by Peter Bacon, who's the Director of System Integration at Peregrine Semiconductor. Now let me introduce our speaker. Peter Bacon serves as the Director of System Integration at Peregrine Semiconductor. He oversees product requirements definition, technology feasibility studies, and application support. Peter has over 30 years of RF product development experience from his contributions at Peregrine, Skyworks, Connexent, IBM, Raytheon, and Harris Microwave. He received his BSEE and MSEE degrees from Lehigh University and his MBA from Boston University. Peter, I'll turn it over to you, and I'm looking forward to your presentation.
All right, thank you, Gary, for the introduction. Today I would like to walk through the general concept of RF linearity and why it is critical to today's ever-increasing data throughput requirements. We will then look at a specific application where high linearity is essential to signal integrity. So looking at the outline for today, go through a brief introduction as to what the general problem is in the marketplace. Then we'll get into implications of the RF channel, and that'll be using Shannon's capacity limit as sort of a backdrop for that. And then we'll get into a discussion both on UltraCMOS technology leveraged for linearity and how it is applied specifically to DOCSIS 3.1. And then we'll look briefly at improved mixture noise performance because that also is a factor in terms of overall RF channel capacity. And then wrap it up with some conclusions. So the issue that we're facing today is data rates continue to increase in virtually every application, from wireless communications to wired broadband. And as things become ever more connected, the data rate just continues to blossom. And so there's a need to improve the data capacity of the channels. We have this quote from AT&T where data usage on the network has increased a whopping 20,000% over the last 5 years, with usage at least doubling every year. And so that happens or impacts the entire network, whether it's wireless, wired broadband, or connected devices. So the need to improve throughput is critical. As we look at how to assess this, Claude Shannon of Bell Laboratories put together a very helpful and really defining presentation of the theory of communication back in 1948, and ultimately it made its way into a book entitled The Mathematical Theory of Communication. And from that, he really helped cement a lot of ideas concerning how we look at communication and assess and measure the quality of communication links. So one of the key things was using a logarithmic measure, since many of the time, bandwidth, and number of relays, that goes back to the telegraphy that he was very much focused on, as well as these vary linearly with the logarithm of the possibilities, different combinations and possibilities of solutions. And then also probability itself was used as a metric for the communication fidelity. So the probability of errors was the dominant metric used to assess different communication methods. He reiterated the base 2 as being a dominant or preferred implementation for communication, and that is simply because it works very well with on-off relays and switch networks. So we have the 0 and 1 concept really cemented through his work. And then he reused 2 keys bit terminology, and that really helped cement in the idea of bits as well as bytes, and then going into nibbles, and even today we're up to yottabytes. So it's really impressive where this is taking us just in the magnitude of data communication and data itself. So looking at some of the specifics of what Shannon defined, he defined a channel capacity limit, and starting with a very basic transmitter to receiver means of communication information. You have the information source, it goes through a transmitter, is received, and along the way it picks up noise, so you have the signal being added to noise, and you have at the receiver the need to separate the signal from the noise, and therefore you're going to have some signal-to-noise ratio. He also took a look at a noiseless channel, a discrete channel with noise, and then came down to the fundamental theorem that really is sticking with us. Many people have worked with this, and it's really a standard in terms of assessing communication capability. And so you have the channel capacity is a function of bandwidth and then log 2 of essentially the signal-to-noise ratio. So you have the power of the signal plus the noise over the noise. And today we've done a little bit of modification on that. We've started with the same basic concept, bandwidth and signal power plus noise over noise, and then we've gone through and implemented some regroupings where we break out the n over n, that becomes term 1, and then we look at this parameter here, which is known commonly as the signal-to-noise ratio. And we can look at this at either the bit level or symbol level, and we can also look at a different, slightly different nomenclature here where we separated out in this description capacity and bandwidth, and we get a sort of a normalized term here, which is the energy per bit over the noise floor effectively. So we can also look at that in the, sort of conversely, if we have targeted a certain capacity or in a given bandwidth, we can then determine what characteristics we need for the signal-to-noise ratio. So this is sometimes used when you're looking at a receiver, what level of energy per bit over the noise is needed at the receiver input to support the capacity that's expected. And then we can also look at what the interference impact is to this by breaking or adding to the noise parameter, basically interference. And this holds as long as the interference is effectively noise-like. And in today's communication systems, many of the signals, if not all, are becoming much more spread spectrum and therefore have very much a noise behavior about them. Broadband, fairly consistent with frequency. So going on, Shannon's limit did assess arbitrary small errors in the equations that he generated, but I want to look a little bit more specifically in terms of how errors are introduced into the system, and specifically in the transmission and reception of the signal. So typically in a transmitter to receiver, we have impairments that show up on the transmitter side, and then likewise impairments on the receiver side. And in between, there are noise sources that affect the overall signal as it goes along. So either simply from attenuation of the transmitter power level or from additive noise coming in, you're going to have degradation of your transmitted signal at the receiver. And a number of different impairments exist. We can think of phase noise, thermal noise, and phase and frequency errors. For nonlinearities, we have compression behaviors as well as basic, that falls into basic P1dB compression, or more specifically AM to AM and AM to PM behaviors. And then we can also have memory effects that are overlaid where a symbol at point end is impacted by previous symbols, so the accuracy of the future signal can be impacted by its present trajectory. And this is distinct from encoding with memory, which is a topic that Shannon also dove into, so I just want to make that distinction here that we're not talking about that. And then intermodulation, where it's a measure of interaction between signals, but it's really a measure of how accurately can your transmitter or receiver maintain distinction between two distinct signals. And then finally, another thing to consider is passive intermodulation distortion, because we're getting into the levels where that can come into play because of the need for getting to ever higher signal-to-noise ratios. So as we look at metrics and looking at the signal accuracy versus noise, there are sort of two ways I look at it. One is with regard to the desired signal metric. Desired signal has its own metrics that really help define its accuracy in terms of what's being produced for the transmitted signal. So you have things like error vector magnitude, modulation error ratio that is looking at the accuracy of the vector that is being transmitted, and that can be assessed either through those metrics or perhaps how it affects the bit error rate. And then a little less specifically to the signal itself, but more how it maintains signal integrity, IP2, IP3, the intermod products, and then also a very specific cubic metric coming from the 3GPP specifications, and looking specifically at the cubic of the signal versus a reference. And then some other metrics that really look at what the transmitted signal is generating in the adjacent channels. So ACPR, ACRL, and ACP, so basically off-channel spectral regrowth. Turning to the other portion or the other aspect, which is the noise, you go from very wideband noise floor type issues from Johnson-Nyquist and the thermal noise floor to generation recombination noise, and then noise from oscillators such as the 1 over F and oscillator phase noise. And then as we'll be looking more today, we get into spurious, and specifically the integrated spurious. Since it's a noise-like spurious, you integrate across a bandwidth to give you a specific power level. Okay, as we look at what's happening in the marketplace in general, channel impairments are really being affected more and more by interference. And this is, I throw up two different examples here. One is the AT&T and FCC interaction that's been happening over the past couple of years, where the FCC is asking or dictating for interoperability between band 17 and 12 units. And what has been historically done is this block A has been vacated to minimize interaction between band 17 and lower bands down here that cover digital TV. Well, this is being asked to be used and be leveraged. So how that's done is an issue. And then looking at public safety, in this range, we have discussions on these small slivers, 1 megahertz of bandwidth that are being suggested be combined to the public safety. So any guard band, 1 megahertz guard band, is basically being absorbed into the public safety band. So the need for bandwidth is pushing away guard bands and making the interference challenge all that much greater. If we look at a specific example for today, it is going to be looking at data over cable. So looking at a cable modem, and DOCSIS is a specification that's put out by Cable Labs that really is used by much of the U.S. cable market to define how the cable modem is to interact with the overall infrastructure. And it really does address the entire cable infrastructure that's needed from the back office network to the interconnect, which is the hybrid fiber coaxial system, and what happens at the cable modem and what is supported for the end user. So it's providing the final connection to effectively the internet through the cable network. Some specifics that have happened with the DOCSIS 3.1 release. This is a release that's now about a year and a half old. In second release, so its current revision was December of 2014. They've moved to OFDM modulation for the downstream. So the downstream is coming from the cable operator to the home, to the end user, to the office. And on the upstream, it's using a variant of that, OFDMA, which is multiple access. So you have the same basic modulation concept, but multiple access is overlaid on top of that. In addition, the frequency range is increasing from a max of just over 1 gigahertz to 1.2, and that is a must. And a may, in terms of terminology within spec, 1.794 gigahertz. Generally, what's limiting this is the infrastructure that's presently deployed. The number of frequency partitions has increased from 3 to 4, and also the ability to select between partitions has been added. And then the QAM modulation has increased from a max of 1024 up to typical 4096, but 16,000 QAM is also being discussed and identified within the specification. And then in general, there's a greater implementation flexibility that has been built into the entire specification. To start off with, to really take a look at the channel impairments, I want to just give a really simple, intuitive look at what's going to happen to the signal-to-noise ratio, just so it's very clear to you as we go up in QAM level that the SNR will be increasing. So very simply put, looking at an impairment, if we have an impairment that's affecting our desired signal, we have the two vectors together, we end up with a signal with impairment. It should be obvious that if we cross this middle line, we've now taken what should be a signal here and incorrectly decided that it's a signal here. So we have 2 bits effectively represented by these 4 signal options. So we've made an error if we go across here. So that should help us define that the maximum impairment that I can absorb should be on the order of 1 if I assume that this is a 1.4 square root of 2 length here. And the simple ratio translates out to 1.5 dB. If we take that to a little more rigor in the calculation, you actually find that 1 in 10 bit error is going to require a 1.3 dB SNR. So the first order, we've got sort of a sense that it doesn't take a whole lot of SNR to give you a reasonable bit error. But if you really want to drive it down to what's required for a communication system, you're going to be down into the 10.8 dB signal-to-noise ratio. Now, if we do that same simple math on 4096 QAM, there should be a factor of 32 there because you've now divided that impairment signal of 1 by 32 divisions here, and therefore you should have at least a 16.5 dB increase in the SNR. So you're going to see a very significant increase in that level. And in fact, when you go out and do the actual numbers, it's more than that. So it becomes even more of a challenge. And much of that has to do with the fact that you have to be very tight across a broader range rather than just the 4 quadrants where you could actually go well beyond and still not run into issues in terms of error. You don't have that flexibility here. So the push on SNR continues to increase. So if you remember the definition of the signal-to-noise ratio, you either increase the power level to improve the SNR or you improve the noise. In this case, we're looking at noise plus interference. This is just a series of increasing QAM levels showing you that we're roughly getting 5, maybe 6 dB increase in terms of the SNR requirements as we jump by a factor of 2 in the bit count, or not a factor of 2, but by 2 in the bit count. All right, so moving on to the upstream interference of the downstream problem that occurs in DOCSIS. The partitioning of the cable is very straightforward. It's a single cable, so you have to support both the downstream and upstream, and therefore you are frequency dividing your bandwidth. And the challenge is to make sure that when you have a upstream signal, referred to as H1 here, that it's spurious, out of band emissions don't corrupt the downstream RX. And in many cases, what has been done historically is in DOCSIS 3.0 and earlier, there hasn't been a need for doing any frequency selectivity or changing during the operation of a cable modem. So quite often there's a filter that's used to do this frequency division right at the F connector of your cable modem. But now we're becoming a little bit more flexible and wanting to be able to make this change on the fly and do that through deploying cable modem boxes over a period of time rather than all at once, and maintain operability while that deployment and final transition occurs. So the need is actually changing in that the equipment is needing to support this when the filtering is actually being reduced or perhaps even eliminated, or where it's located is being changed. So what is shown here is the out-of-band emissions that could come from the TX path or circuitry and how it corrupts into the downstream frequency range. Going a little bit further in terms of architecture, the filtering options that are presently being considered sort of fall into two camps. One is what I refer to as full frequency, and it requires an F connector switch right at the cable input. And so this doesn't have any filtering on this side of the cable drop, and therefore it needs to maintain the frequency duplexing that is established by these two filters, low pass and high pass, basically a duplexer diplexer architecture. So the challenge becomes in the linearity of this part needing to be maintained so that the corruption of the downstream band doesn't occur. The second architecture is a little bit more driven perhaps by cost and less by performance, because in this architecture, this new box has a single downstream filter, and so as these are deployed, effectively the downstream that's presently defined, which would be roughly below this frequency range. You can see here it's downstream here is 54 to 1218. We lose some of that frequency range, the 54 to 108, by doing this architecture, and hence the partial frequency. What this does do, though, is it eliminates the harmonics from the switch and leaves this switch exposed just in a small section of frequency range, and I'll get into the detail regarding that. So as you send a transmit signal through this path, the switch and all of the harmonics of the transmit chain are addressed through this low-pass filter. But then that same transmit signal hits the switch, and its linearity will dictate how much harmonic generation, intermodulation, is generated through this bandwidth. So you have basically from the 42 megahertz to the 85 megahertz where things get through to the infrastructure that's already deployed. So out onto the cable, and you begin to affect legacy cable modem boxes. So the transmit signal from going through the switch generates second and third harmonic. That comes through this filter, gets a little bit abridged, as shown here that the third harmonic gets cut in and not going its full extent in terms of frequency range. And then when it comes in here, the low end, the TX, is actually cut out at the low frequencies, but you are still effectively jamming or interfering with the downstream receive of the legacy box. So the reason for that problem is you basically have a hole within the filtering between this filter covering up to 42 megahertz, and then it's actually vacant until the 85 megahertz cutoff of this frequency this filter begins to impact or clean up the harmonics from the switch B. So the switch B is the most critical in that architecture. Now, how do we assess what's needed from a switch performance? And what is needed is to both understand the switch capability performance-wise, and then second of all, be able to translate that into the requirements of DOCSIS 3.1. So what is shown here are three different switch performances, looking at IP2, IP3, second and third harmonics. And in this first set of tables, we're looking at the intermods with a 18 dBm tone that happens to be closely related to the power level needed for the DOCSIS specification. And what is shown is there are two peregrine switches that are shown here that are performing differently than one another. One is significantly lower than the other, the 722 versus the 422, and then benchmarking against other SOI that it in turn is worse than the two peregrine switches. And the same holds on third harmonic and holds also obviously on the IP3, IP2, given the interrelationship of the metrics. Now, with this data, the ideal would be to map this into the actual specification requirements for DOCSIS. And a key spec from that is the integrated spurious. So thinking back to the signal-to-noise ratio, taking the noise component and defining that as noise plus interference. This is basically the interference level that we're looking at. We're trying to understand the impact of the interference level on the overall signal to noise. And in fact, sort of translating that through the spec, we end up with requirements that are pretty well defined within the DOCSIS specification. So what we'll be looking at is taking this nonlinearity behavior and then mapping that into a spurious simulation. And the way we address that is we define the switch in terms of a Taylor series expansion. So we take the second and third order terms and model this behavior through the Taylor series expansion. From the DOCSIS 3.1 specification, you can see here under the integrated spurious section of table 7-6, there are different levels depending on frequency, and from minus 35 dBmV to minus 45 dBmV. This is over a 4 megahertz frequency range in the receive path or the downstream path. On the upstream, we're looking at the entire bandwidth of 5 to 42 megahertz. So with that specification, you can map that into requirements here in terms of bandwidth, and specifically map it with the TX signal that is basically an ideal baseband signal that's been mapped into the appropriate frequency range. So we have an ideal baseband signal, and we pass that then through the nonlinear switch model. And when we do that, we begin to see the impact of the different switch performance levels that against the requirements. This is the raw numbers from the specification, and this is a 10 dB back off. The idea being that you're easily going to use up this 10 dB in any variation in manufacturing, or more likely, as we go to even higher SNR levels, we're just going to be pushed all the more for better performance. So this is shown here that for the 722, we are meeting requirements across this entire range, and then for the 422, it falls short on the area here. And we'll show in a minute that this is closely correlated to the second order term and its behavior. With this model, one thing that we would like to do with this model, once it's been validated, is to then go through a design optimization. So this guides the design team to target new performance requirements for a switch that would be more ideally suited for meeting the DOCSIS requirements. So what we can do is go through a number of simulations that show the behavior of the model versus requirements. And looking here, we have both the second in the blue and then the third order harmonic order nonlinearities defined. So we're looking at both from a harmonic as well as an IP3 perspective and seeing the behavior. So these are mapped together, meaning the best performance is in the first column in each of these. So it's showing very good performance, and then I back off 10 dB and 5 dB respectively, and look at the response coming from the related simulation. And what you can see from this is that the second harmonic will dominate this area, and then the third order term affects the higher order. It happens to be that with the frequency ranges defined at 42 megahertz, you take a 2x of that, you're up to 84. And you can see that it's going to have some impact here, but dominant factor in this range is going to be the third order, and in this range is going to be the second order. So with that information, you can then go through and define the optimum combination of the second and third order terms. And this is shown here in the gold color, that targeting from a H2 and H3, the harmonic levels, we want to be at minus 120 and minus 140 dBc, respectively, at the power level required. Now, how do these numbers translate or compare it to some other standard metrics? And I'm used to seeing regulating entities require any wireless system to meet. And here you can see that we're easily 20 dB below that number, and even at the 1 watt level, we're 40 dB below that number. So these numbers are not simple. They're quite challenging and need to be carefully assessed and addressed in terms of the design. So a question then comes, can the basic device technology support these requirements? So I'm going to step back from active device and take a look at the substrate itself. So this is a simple RC model of a SOI substrate. You have a box capacitance that's associated with the active layer, and then we also have a capacitance that's associated with the handle substrate or wafer, whether it's silicon or sapphire, and then a finite conductance of that substrate. And what you see here as the GS is changed from being a very high resistivity down to basically a bulk silicon, that there is a reduction, I should say an increase in the frequency at which the substrate changes from being seeing just these two capacitances to seeing just the box capacitance with the resistance. Likewise, on the substrate, you can see here the Q factor, or more importantly, the substrate frequency, resonant frequency, also decreases as the resistivity increases. And you may wonder why we want that, or what's the benefit of that. And if you look at these frequency ranges, we're very close to the band of interest here, in the sense of DOCSIS is running in the megahertz range for the transmit path. So there is need to make sure we have a very consistent behavior here. Another metric that we've used on actual hardware is measuring a transmission line. This is a 1.1 millimeter coplanar waveguide microstrip line. Rephrase that, transmission line, 50 ohms. And what is being measured is the insertion loss versus input power, and this is at 915 megahertz. And you can see that it's very consistent. This is a through line just for calibration, and then looking at 3 different technologies. We have in the blue the high resistivity SOI. Then we have in the greenish color a trap-rich SOI, and then thirdly silicon sapphire. So that is results for insertion loss. And then going on to more of the substrate implications, this is looking at the second harmonic input power versus the substrate technology, as well as the third harmonic. And what is shown here is, again, in the blue, the high resistivity SOI has a behavior shown that's about 40 dB worse than the trap-rich, and the trap-rich itself is about 20 dB worse than the sapphire-based substrate. A very similar story on the third order harmonic. And therefore, the question sort of falls out, well, what does DOCSIS need? And DOCSIS is very stringent on the H2 and H3 requirements. And again, minus 102 dBm for the H2, that aligns with the 120 dBc. And likewise, 140 dBc translates to minus 122 dBm for the H3 component. And when we map those two, we see that it becomes a challenge for other technologies to really meet this requirement just from a pure substrate perspective. And again, this is a transmission line that's being measured, so you could go through your thinking that there's not going to be a whole lot of transmission line, but fundamentally you're talking about a device, a switch that's probably on the order of a millimeter in size, and therefore you've got the component from the substrate coming into play with the particular application here for DOCSIS. So as we then take that information, apply it back into measured results for an optimized design, the question is, do we actually reach targets, and can we support the requirements that are needed? So this is looking at both IP2 and IP3 targets, and they map into 132 dBm and 78 dBm. And then likewise, the corresponding H2 and H3 levels are minus 120 and 140. So looking at the harmonic level of minus 140, 120, These are the measured results, with the black line being the target level for what our previous design was, the 722, and then an optimized for the specific target. So not a big change in the second harmonic, very stable across frequency. And then on the third harmonic, we're very much up against the system level, but it would appear that we are being consistent with the requirements, that we're tracking the system level, and at least the high and low end frequencies we're meeting numbers, and we're right on the system level. So first order, we would say that we're very close to those requirements. And then conversely, looking at the IP2 and IP3, here's a fairly significant, it's not dramatic on the scale here, but we're at least 5 to 7 dB improvement, the yellow being the optimized design from what the previous version was, the green line. And so that's very important, because this is very much where the transmit signal is being generated in the tens of megahertz as opposed to hundreds of megahertz. And then where we've trimmed performance, this is sort of excess performance the previous design had, trimming basically about 5 to 6 dB, but still being considerably above the requirement that's needed to generate minimal interference that would degrade the downstream. Right, then turning to noise. This is just a brief slide covering noise, because that is another factor, obviously, in the signal-to-noise. So the emphasis so far has been on linearity, but we clearly have an interest in noise performance. And we've demonstrated some improved mixer noise performance, and this is noise behavior under blocker conditions. So we're reducing the susceptibility of the mixer to being influenced by a strong blocker. So we've gone from an existing 4150 to a 4152 architecture, added functionality, and shown over here is the improved mixer noise floor with an RF blocker applied. So with the same level of RF blocker, we've got on the order of 5 dB improvement in the overall noise performance under a number of different test conditions for the mixer, looking at different frequency ranges and power levels for the LO. So in conclusion, data rates continue to increase. There's a demanding need for both bandwidth, more bandwidth, and SNR levels to improve and increase. And that's simply because they're directly related to overall capacity. The easiest way to increase capacity is with bandwidth, and when you can't get any more of that, then you need to increase the SNR to make the throughput of the bandwidth even greater. And DOCSIS 3.1 was used as an example where linearity is essential and an essential factor in meeting the requirements. So we saw the increased interference that will degrade the SNR levels because of the interference, but we also saw the increasing SNR requirements because of the increased QAM, so that it's really being driven by two things. The modulation complexity is driving the SNR higher, and then the need for switches at the front end of the cable modem is eliminating the ability to filter much of the interference that would otherwise be generated. And then we've gone through a detailed analysis that defines the performance requirements and applied that to an optimized design. That design has resulted in performance that's more optimized for DOCSIS, giving better coverage of the entire frequency range for the transmit path. And we've showed benefits of the UltraCMOS technology in meeting those requirements. So specifically the single-pole double-throw switch for the 120 dBc and 140 dBc second and third harmonic. And then also in the last slide, the mixer noise performance for the 4152. So I want to thank everyone for their time today, and at this time, take any questions that you may have concerning the topic and material.
Peter, thank you. That was a very informative and I think excellent presentation. Covered theory as well as obviously the practical application in a major market evolution with DOCSIS 3.1. So we do have time for questions, so I would encourage those of you that are watching the webinar, if you have a question, feel free to enter it in the Q&A box to the right-hand side of your website, your WebEx screen, and we hopefully will have time to get to those. Let's start with one question that comes, does the harmonic behavior of each technology hold for higher frequencies?
I can speak specifically to what Peregrine has looked at, that both the device behavior and some of the techniques that are used to get to different power levels have been shown to hold up through the, say, 20 to 30 gigahertz range. So the fundamental behavior remains consistent across quite a broad range of frequency.
Okay. You talked about the using the Taylor series in order to model the device. How was the Taylor series model actually generated?
It was used by looking at or generated by measuring actual devices. So and when I say devices, actually looking at switches and full product and characterizing them for second and third harmonic, as well as IP2 and IP3, and coming to a consistent definition in terms of the coefficients for the Taylor expansion that held across all the measurement results, and then taking that as the model definition.
So you kind of do like a least square fit?
It's more effectively just looking at the harmonic levels and getting the Taylor series components to fit that.
Got it. Another question, why are you concerned about the substrate behavior at these low frequencies?
Well, with DOCSIS as the example, we are transmitting across megahertz of frequency range, so just having a substrate that behaves consistently across that range is very helpful. And then also the primary reason is shown in the harmonic measurements, where it's 20 dB better than the trap-rich SOI. That just takes it further out of the picture, and you become much more dependent upon the fundamental switch device rather than the substrate.
Okay. On the PSD plots, what is the bandwidth and the center frequency of the applied input signal?
The input signal is a 24 megahertz bandwidth signal, and if I recall correctly, it's going up in terms of its upper band edge right to the 42 megahertz range.
Okay. Again, we have some time. If folks have questions, feel free to type them into the little Q&A box to the right of your screen, and we'll be happy to try to answer them. Another question, does Peregrine actually offer foundry services for any of your processes?
Not as a general service. We consider opportunities as they arise, but in general, there's not a foundry service.
Okay. You talked about the DOCSIS 3.1 standard, and I don't recall whether you talked about the modulation. Can you speak a little bit about the potential data rates that DOCSIS 3.1 will support?
I don't have those off the top of my head, but I know it's in the gigabit per second type range.
It's getting up there. Maybe
yeah.
Giving fiber a run for the money?
It's being used over fiber, so yes, it's being leveraged.
Okay, I think we have a few more minutes, and if anyone has a last question before we end, please feel free to type it in. Otherwise, we will wrap things up. One question someone asked about the slides. Yes, everyone who's registered for the webinar will get a copy of the slides. You will see that here within the next half hour. You'll get a link that you can actually go to and download the slides. One other question that's come in, why does the SOI quality have an influence on the noise level?
Yeah, I think it's more of the mixer application. It's more fundamentally circuit design, as opposed to being a contributor to the noise. I don't think there's any impact on the noise itself from SOI versus Sapphire. It's much more the circuit contribution.
Okay. Have cable systems historically led the way in high SNR usage? And if so, what does DOCSIS 3.1 imply for cellular or Wi-Fi or any of the other wireless systems?
I think you can, I don't want to say exclusively, but certainly it's been a driver in terms of QAM, SNR, so forth. And it's usually looked at as being one of the more challenging specifications to meet from a linearity perspective, communication, definition, link budget, so forth. It's a little harder to dictate or understand how you would translate this into other standards that may have other constraints, such as a handset has limited battery, and therefore it may not have the luxury of going to really high QAM quickly, but may have to use other techniques such as just greater cell density to provide the increased throughput that's needed.
I think I've heard some folks talk about point-to-point radio systems are kind of going at 1024 going to 2048, but I think that's about the highest I've heard.
Yeah, this is the first time I've heard the 16,000 QAM even mentioned.
Yeah, that's amazing. So let's wrap it up here. I don't see any more questions in the queue. I want to thank Peter Bacon for an excellent presentation and walking us from the system level all the way down to the component level. Again, for those of you that have been listening, you will receive a copy of all the slides here within the next 30 minutes or so. And also, we've recorded the webinar, which will be available to view in the events section of the Microwave Journal website, and it should be up within 24 hours. So if you found this informative, please let your colleagues know so they can watch it on demand, and if you missed any part of it, you can go back and watch it again. So thank you for joining us, and have a nice day.